Good afternoon. So this is our 25th lecture. So yesterday we started our discussion on the momentum equation, and from the Reynolds transport theorem, simply we know that summation of df is equal to integral over the control volume del rho v vector into dv bar plus integral over the control surface rho v vector dot n cap into dv. Okay. Now the simplest simplification of the first term after the integral is nothing but uh, del rho v vector divided by del t times dv bar, which is nothing but equal to uh, del by del t of rho v vector into dx dy dz. Okay, so up to this we have done. Now there was the question which I asked you people, whether whenever I will be considering the momentum in x direction, whether I should consider the component of the velocity or velocity vector. Okay, so typically if you see, this particular term is nothing but representative of the momentum flux across the control surface. Okay, and for a control surface, if you see from the Reynolds transport theorem, so integral over the control surface is nothing but rho times v vector. So this v vector over here is nothing but representing the vector of velocity, and rho v cap n cap is nothing but equivalent to v dot n cap into dA is nothing but equivalent to mass flow rate. Okay, so the necessary condition for the mass flow rate is that you must use only the normal component of the velocity to the interface, but whenever you are considering the momentum, you have to consider their total momentum which is entering at the x. Okay, is this point clear?
V vector dot n cap, it is representing the velocity which is perpendicular to the surface area.
Yes, yes.
So there it will be component velocity.
Yes, u.
But rho into V, that V will be full.
Yes, yes, of course. Okay, because that is a simple v vector. It is not multiplied with normal. Fine. Is this point clear? So that's why now what we will be having, we will be having net rate of momentum change in x direction. So you can see that m dot x into v vector was the momentum entering, m dot x into v vector plus del by del x of m dot into v vector into dx. This will be the rate of change of momentum. Okay, so if you do this rightward momentum minus leftward momentum in the x direction, so then you will be finding del by del x of m dot x into v vector dx, and m dot x is nothing but equal to rho u times area. So for x direction, area is dy dz and it is independent of del by del x. That's why I have directly taken out. Fine. Up to this point, is it clear to all? So similarly, the way I have momentum in x direction, I will be having momentum in y direction also, and I will be having momentum exchange in z direction also. Is this point clear? So now, the net rate of momentum change in y direction is nothing but equal to del by del y rho v vector dx dy dz, and then I will be having in z direction as nothing but rho w v vector into dx dy dz. Okay, so now what I will do, I will substitute. So you can see that this element is having 3 directions only, so 6 faces, and we have covered all the 6 faces. So it means my this second term integral over the control surface is now resolved. Okay, so once this second term is resolved, I can substitute into the main equation, and I will be finding sum of all the forces which are acting on this differential element. That will be equal to del rho v vector by del t. Okay, it is having dx dy dz with it, and all other terms are also having dx dy dz, so that I will take at the end only. So I will put a bracket at the starting. So into del by del x of rho u into v vector plus del by del y of rho v into v vector plus del by del z of rho w into v vector and times dx dy d. Fine. Now what I can do, I can apply over here the chain rule in order to simplify this equation, and if I do so, then ultimately I will be getting that v vector times del rho by del t plus rho times del V vector by del T. Okay, is this one clear? Plus rho u times plus V vector times del rho u by del x plus rho u times del V vector by del x. Correct? Sorry? No, I am applying first over here chain rule over here. Okay, so this will be V vector times del rho u by del x.
Rho u into that will become u one.
Why it will become u? This is a V vector, na?
V vector is ui plus vj plus
Velocities can vary in y and z. Okay. Okay. Is it correct? So this is only the first term now. Now the second term. What will be second term? Plus V vector into del rho v by del y plus rho v into del V vector by del y. Okay. Plus V vector into del rho w by del z plus rho w into, fine. So this we will be having, and this times dx dy dz. Now if you take these terms, first is V vector into del rho by del t, and here also V vector is common in this term and this term. Okay, so ultimately what I will be getting, sum of all forces in f direction is equal to V vector times del rho by del t plus del rho u by plus del rho w by del z plus rho times del v vector by del t. Okay, plus rho u into del v vector by del x plus rho v into del v vector by plus rho w into del v vector by del z. Okay, so this whole outside will be dx dy dz. Now can you tell me what is this term? What is this term? Continuity equation. Yesterday we have derived. So this entire term is nothing but equal to continuity equation. So this must be equal to 0. Okay. So what I will be getting then, sum of all forces is equal to rho times, rho is coming common in each and everything, rho times del v vector by del t plus u times del v vector by del x plus v times del v vector by del y plus w times del v vector by del z. Okay, times dx dy dz. Okay, is this one clear? So ultimately what I will be getting, that sum of all forces is equal to rho times, how I can write this term? This is temporal derivative and convective derivative. So this is nothing but total derivative of the velocity vector. So rho times total derivative of the velocity vector into dx dy dz. So over here if you see, this first term is nothing but convective acceleration, and this term is local acceleration. So convective plus local is total or substantial derivative or total acceleration. Okay. So ultimately we have got the fundamental thing only, that rate of change of velocity is giving us nothing but the time rate of change of velocity times mass of the fluid element is giving us the sum of all the forces which are acting on this differential fluid element. Okay. Now can you tell me what will be the forces acting on this differential fluid element? If I have to calculate this term, sum of forces, what will be? First will be surface force. Anything else? plus body force. Okay. So these will be the two set of forces which will be acting. Okay. So one will be surface force and second will be body force. Now, what will be body force?
So, sir, but can you explain the two types of acceleration?
So in this term, if you see, this is representing the acceleration which is because of the spatial change in the flow parameter. Okay, so if velocity changes with x direction, y direction or z direction, okay, so whatever the effect is caused by that on the acceleration of the flow, that we call as convective acceleration. Okay, whereas the acceleration which is we are considering a fixed point in the flow domain, but we are measuring that if any change at that point in the fluid flow velocity is happening with time, that we call as local acceleration. Okay, already I have discussed convective acceleration and local acceleration before mid-sem slide. Okay, so now we will be having some of the two forces which will be surface forces plus body forces. Okay, so if I neglect that I don't have any electric or magnetic field present in this system, then my body force will be solely because of the gravity. And what will be body force? Density times volume of the element, dx dy dz times gravity. So this is my body force which is acting on this. Okay, and of course this force will be acting only in which direction? So k cap minus k cap I must put as a unit vector over here. Okay, so if k cap is unit vector in positive z direction, then minus k cap will be in the downward direction. So this is the one body force. Now what about surface forces? Pressure and viscous. So important point is, till now whenever we were actually studying the surface forces, we were only measuring the effect of the pressure force. Okay, either we were telling that surface force is included as a whole total term, or it is included only because of the pressure term. Okay, so viscous term is something which we have not dealt with that much clarity. Okay, so typically what we have to do is, if I consider this fluid element again, if I consider this fluid element again, dx, dy, dz, so here it will be having some stresses on this. Okay, so what type of stresses it will be having? So first you can see this left face in x direction. So left face in x direction can have a normal stress. Okay, so I am, which plane I am considering now? This particular plane. Okay, so in this particular plane, one will be normal stress. Okay, and so if I have to designate that I am calculating the stresses on this plane, then with this sigma, first I will be using one subscript. So this first subscript refers to the plane. This is to designate the plane on which we are calculating the forces. Okay, so perpendicular to this particular face we have x direction, that's why I am calling it as x plane. And then along with this I have to also mark that this stress is acting in which direction. So of course this stress is also acting parallel to the x direction, so that's why I will be writing it as sigma xx. And let me show it with the tensile nature. Say this is my sigma xx over here. Okay, is this one clear? So of course, a fluid element can have two types of stresses. One will be normal stress and other one will be the shear stress. Okay. So whenever we have to designate the normal stress, we have to define two things. One is the direction in which the stress is acting, and second thing we have to define is plane on which it is acting. Okay, so particularly the first one I am referring to over here as plane, and second one I am referring to the direction in which this stress is acting. Okay, now this is the left face. This particular left face can also have some shear stress in downward direction. Okay, it can also have some shear stress in downward direction. So I am representing that as tau. And this tau is acting on which plane? Plane. Plane is the same. So x plane, but what is direction? Is it y? So direction is, this is x, this is y, and this is z. So it is acting in z direction. So it will be tau x z. Okay. Then what will be other thing? On this I can also have a shear stress in this direction, parallel to this, parallel to along the y direction and parallel to the face. So that will be nothing but tau xy. Point is clear? So it means that if I have to define the stress state of a fluid element, so 3 are acting on a single phase. Okay. Then similarly, there will be next 3 on this face, 6, 3 on this back. How much? 18. Okay. Sure. Whenever we define a stress tensor, so what we have? If 3 to power 0, I am having a 3-dimensional system, 3 principal axes. So if 3 power 0 is there, that means 1. So this is nothing but 0th order tensor, which is a scalar. So scalar require only one component. Okay. Sorry. Yeah. If I have a vector, then 3 to power 1, which require 3 components. If I require a tensor, then how much? 3 to power 2, which is 9. So total I will be having 9 elements. How I will be having 9 elements? Because if I say that a fluid element is at rest or fluid element is in equilibrium, because we are talking about the fluid element in equilibrium. So if I say my fluid element is in equilibrium, then whatever the stresses are acting on left face, same amount of magnitude will be there for the stresses acting on the right, opposite face. Okay. So here also I must say that I have sigma xx, then, sorry, direction I must write opposite, tau xz and tau xy. Fine. So is this point clear? So now front and back, only these are having 3 required components. Okay. So similarly, this will be for other faces. If I write 3 3, then it will make total 9. Okay. So ultimately, I can say that in this system, if my sigma is the tensor, so I am writing sigma as ij, where I represents the plane and j represents direction. Okay. So this sigma ij will be having actually 9 components. So one component will be sigma xx, sigma, or in place of sigma actually it will be shear. So say here I am representing with tau. So shear will be tau xy, tau xz. Okay. Then I will be having here sigma yy, tau yx, yz. Then here I will be having sigma zz and tau zy. Okay. So this is how I can actually write down my stress tensor. So it means that if I have to calculate the forces, before knowing the forces, I must know my stress tensor also. Okay. So at the moment what I am doing, I am writing it in the generic sense. So please make one clear difference. Whenever I am referring over here sigma, sigma is nothing but representing the total normal stress acting on the element. Okay. So sigma is representing the total normal stress. And when I am writing tau over here, so at the moment tau I have only considered for shear stress, but tau can also have normal component. Okay, so basically this sigma over here will be nothing but hydrostatic term. So what will be the total normal stress in a system? So total normal stress in a system will be because of two components. First is hydrostatic plus second is viscous. So there can be viscous normal stress, okay, as well as the hydrostatic viscous stress. Point is clear? One will be because of the pressure. So pressure component which I am considering, that I am referring to as hydrostatic normal stress, and there can be some normal stress because of the deformation of the fluid element in the normal direction. Okay, so that is coming as the viscous normal stress. Fine, that will be coming as nothing but viscous normal stress. So that's why whenever I am referring to tau symbol will include both shear viscous stress as well as the normal viscous stress. Is this point clear? Please tell me. Okay, that if you recall, I had shown you the linear strain of a fluid element. What was the linear strain? Del U by del X. Okay, so for a Newtonian fluid, if I multiply linear strain for a 1D element with viscosity of the fluid, it will be becoming stress, not shear stress. Whenever I am referring to the normal strain, then it will be becoming normal rate of strain, then it will be becoming nothing but normal viscous stress. Point is clear?
You are just calculating the strain in the normal direction and then you multiply by viscosity.
Yes. So at the moment, what you people have to understand, at the moment simply you people have to understand is that this is our total stress tensor. Okay. And total stress tensor includes the normal stresses which are along the diagonal and the shear stresses. So for the time being, just remember this thing only. This whole thing I will explain you again in the subsequent discussion. Okay. This point is clear. So say this is my total stress tensor. Now how to define this total stress tensor, that we will discuss one by one. Okay. So if this is my total stress tensor, now can you tell me what will be the total force acting in x direction because of the total surface force in x direction? What will be total surface force in x direction? So you can see sigma xx is the normal stress acting in x direction. Okay. So here also I have to consider the same thing. If this side it is sigma xx, this side it will be becoming sigma xx plus del by del x of, if there is some differential change, that is del by del x of sigma xx into dx. So I can say that the net normal stress in the x direction is nothing but del by del x of sigma xx into dx into area. What is area? dy dz. This is the one force. Other than this, is there any other force? When you will be talking about this top surface, what is this top surface? It is a z plane. Okay, so it will be having some shear stress acting in x direction. So that shear stress will be nothing but tau zx. So if I can say that tau zx is here, then this will be tau zx plus dou by dou z of tau zx into sorry dz. Yeah. And this is acting on which area? dy dx. Okay, so it means then I have plus del by del z of tau zx into dz dx dy. This is one. Then what else I will be having? Now this I have a y plane. On this y plane also I can have some shear stress in x direction. Okay, this is my y plane. Normal to this is y plane. Okay, so can I have some shear stress on this plane in x direction? Sorry, y plane I am marking wrong. This is my y plane. Yeah. So I can have some shear stress in x direction. This will be my tau yz. Sorry, tau yx. Okay. Point is clear? So at the other end it will be tau ix plus del by del y of tau ix into dy. And then area will be coming dx times dz. Fine. So it means I will be having one more term over here plus del by del y of tau, tell me, yx times dy into dx dz. So this is nothing but the only contribution of the surface force in which direction? X direction. Till now I have only considered the x direction. Now I will be considering df surface in y direction. Please tell me from the analogy. Del by del y into sigma yy dx dy dz plus del by del x into tau will be on x plane but in y direction. Please understand this point very clearly. Okay, so if you are not understanding, then you will be finding difficulty in doing this. Plus del by del z tau on z plane but in y direction dx dy dz. Fine? All are fine with this? And ultimately I will be having similarly the force, surface force in z direction, and that will be del by del x of tau on x plane but in z direction plus del by del y of tau on y plane but in z direction plus del by del z of sigma zz, and outside I can write dx dy dz. Point is clear? So it means we have accounted for all the surface as well as the body forces. Okay. So once we have accounted for all the surface and body forces, I can write my momentum equation as, so you can see this is the equation number 1. So I can write this equation number 1 as nothing but rho times dx dy dz into dv vector by dt. Okay, is this one clear? It will be equal to first body force is rho g, say dx dy dz I will write at the end only, so rho g times minus k cap, okay, plus force in x direction is this one, surface force, del by del x of sigma xx plus del by del y of plus del by del z of tau, and this will be I cap because this is a vector equation. Okay, plus del by del x of tau xy del by del y of sigma yy plus del by del z of, okay, times del by del x of xz sigma zz times k into dx dy dz. So dx dy dz will cancel out. So ultimately whatever the remaining term is there, that is nothing but the a vector equation, and this vector equation is our momentum equation. Okay. Now of course this vector equation I can also write the component wise. If I take all the I cap terms together, j cap terms together and k cap terms together, then it will be becoming nothing but a simple component wise equation. Okay, so let me write now the component wise. So now next I will be writing x momentum equation. So tell me, now right hand side is very simple, I have already done, but left hand side is the actually thing which you have to think. What I will be getting? Before that, let me show you the expansion of dv bar by dt. This is nothing but del v vector by del t plus u times del v vector by okay. So out of this, whenever you will be substituting the v vector equal to u I cap plus v j cap plus w k cap, this you have to substitute over here. What you will be getting? Rho times, now I am saying only you have to consider the x component. Okay, so if you have to consider x component, you have to consider only the u term. So rho times del u by del t plus u times, out of this velocity vector, which component you have to take? Only u component. Okay, so del u by del x plus v times del u by del y plus w times del u by del z equal to, out of this force only we have to consider the I component. Okay, so what is I component? Del by del x of plus del by del y of tau yx plus del by del z of tau zx. So this is nothing but your x momentum equation. Okay, so if yes please. Okay, so this is nothing but my x momentum. So please remember that our generic equation is this one only. Okay, our generic equation is this one only, but this generic equation is nothing but a vector equation. Okay, so as this is a vector equation, this vector equation will be having single individual components. So one of its component in x direction I have written as this term, and its component in y direction, please tell me now what will be component in y direction. Now it's very simple. Okay, have I written it correctly? Here what I will be getting? Please tell me. xy. Okay, and finally I will be having the z momentum equation plus tau xz. Up to this, is it clear? Anyone is having any doubts? So these set of equations are called as actually either Cauchy's equation, or this is also called as Navier's equation. Navier's equations. Okay, so these are either Cauchy's equations or Navier's equation. Is this one clear? Now, these three equations are nothing but the very generic form of the equations which are applicable for each and every type of flow situation and for any kind of fluid medium. Point is clear? Whether you have Newtonian fluid, non-Newtonian fluid, whatever type of fluid you are having, you can apply this equation. Because till now, what is the assumption of Newtonian fluid? When our stress becomes proportional to strain, then only we say the fluid is Newtonian. So till now, my equation is actually in the form of stress only. Once I have not substituted the formulation of stress, which is a fluid specific one, till that point this equation is nothing but generic one. Okay, so this generic equation is actually applicable for each and every type of fluid medium. Is this one clear? Whatever fluid medium you can take the steady flow situation, unsteady flow situation, okay, whatever situation you are having, actually you can apply this particular set of equations. Okay, now one simple set of equations. Okay, before that, let me first show you the formulation of stress. Now comes the important part. Okay, so what I will do, I will say that whatever the formulation now I am showing, I am specifically talking about now for the Newtonian fluid. So for Newtonian fluid, I can say that sigma ij is equal to minus p plus lambda times del ui by del xi into delta ij plus mu times del ui by del xj plus del uj by del xi. Okay, so now this is nothing but your equation which can represent the value of stress. Okay, so which can represent your stress tensor. So first thing you have to understand is stress tensor is nothing but equal to one stress is coming because of the pressure, so that is accounted for over here, the stress which is coming because of the pressure. Whenever I have defined the stress tensor sigma, I have taken it in outward normal direction to a face, but pressure is always a compressive stress because it acts into the plane of the fluid. So that's why I am writing over here minus p sign. First point is clear. Second point is, when you are having a fluid medium, that fluid medium can deform in linear direction. It can deform in linear direction. Okay. And what was the deformation of the fluid in linear direction? Deformation of the fluid in linear direction, or rate of deformation of fluid in linear direction. So if you recall my previous lecture where I have talked about linear deformation, so you can say that the rate of linear deformation in x direction was del u by del x. Rate of linear deformation in y direction was del v by del y, and rate of linear deformation in z direction was del w by del z. So if I am having some rate of strain, sorry, not rate of deformation but rate of strain, I have to say over here. So if I am having actually strain, then corresponding to that strain I will be having some stress also. Okay, but from this strain, if I have to calculate the stress, then I must multiply some terms, some constant, okay, of proportionality. For example, you have Hooke's law in solid mechanics. So what is Hooke's law? If you have to write stress, it is nothing but Young's modulus times strain. Okay, if you have to talk about in shear form, then shear stress is equal to modulus of rigidity times gamma strain, shear strain. Okay, So in case of fluid also, we should have some modulus of elasticity kind of constant, which will be helping us in developing the relationship between stress and strain. Okay, so there are two constants for fluid medium, and this constant is called as, lambda is called as second coefficient of viscosity. Okay, so mu you already know, it is nothing but our dynamic viscosity, but lambda is equal to second coefficient of viscosity. So other than dynamic viscosity also there is some other term which is actually involved in this formulation. Okay, so that term we call as nothing but the second coefficient of viscosity.
So what's delta I?
I will show you now. Okay, so this term and this formulation, if you see, this is del u by del xj plus del uj by del xi. So this particular formulation I am referring to, and let me make it general only. So in place of this, let me write it divergence of velocity vector. Okay, so because divergence of velocity vector, it will nothing but account for the total volumetric strain. Okay. What is divergence of velocity vector? Now in the previous lecture we have seen it is nothing but continuity equation or conservation of mass equation for steady incompressible flow, but in the previous lectures I have also told you this is nothing but equal to volumetric dilatation. Okay, but what is this term? If you recall, what is this term? This is nothing but the term which represents the deformation of the fluid element. Okay, so deformation of the fluid element will give us nothing but shear stress. Okay, point is clear? So now let me tell you how I can actually calculate this. So what I can do, I can refer first sigma xx. So when I have to calculate sigma xx, what I will be doing at that time, for calculating sigma xx, let's put it in the vector notation only. So what was that? Del ui by del xi. Okay, so when I am calculating sigma xx, I will say that my I is equal to j equal to both are x only. Okay, so I is becoming equal to j. So this sigma xx will become minus p plus lambda times del I and j both are same, so it means del u by del x. Okay, into delta ij. What is the meaning of delta ij? Sorry, I have written this term wrongly. This has to be gradient of velocity vector, sorry, divergence of velocity vector only, because this will be coming because of the volumetric dilatation. Okay, what is delta ij? When I is equal to j, at that time delta ij will be equal to 1. This is called as Kronecker delta operator. Okay, the meaning of Kronecker delta operator is when I is equal to j, at that time delta ij is equal to 1, and when I is not equal to j, then delta ij is equal to 0. Is this point clear? So when I am talking about this sigma xx, corresponding to this I have considered I is equal to j. So if my I is equal to j, then this delta ij will be equal to 1. Is this point clear? So value of this will be 1 plus mu times I j. So it means del u by del x plus del u by del x. So ultimately, what I am getting now, the value of sigma xx. Sigma xx is becoming equal to minus p plus lambda times divergence of v vector plus 2 mu times into del u by del x. Is this point clear? So over here, this you can see, this is nothing but our thermodynamic pressure. What is this pressure? Even if fluid is at rest, then also molecules are vibrating and applying certain pressure on the fluid medium. So this is the contribution of the thermodynamic pressure in our normal stress, and these two terms are coming because of the contribution of the viscous normal stress. Is this point clear now? Why normal stress can be because of the two components. So I will be having normal stress because of the two components. First, because of thermodynamic pressure, and second, because of the viscous normal stress. Is this point clear? Remember one thing, whenever I have considered the gravity term already into the body force, I should not include gravity term in this formulation of pressure. Okay, so even if I am measuring the pressure at the bottom face of the element, I should not include at bottom face pressure plus rho gh. Why? Because rho gh comes because of the weight of the fluid, and that I have already accounted for in the gravity term. Okay, so that's why I am writing it as thermodynamic pressure. So in thermodynamics, pressure is directly related to density and temperature. Okay, point is clear? Is this point clear? How I can write sigma xx? Sigma xx is nothing but minus p plus lambda times divergence v plus 2 mu into del u by del x. Now lambda is called as second coefficient of viscosity, mu is called as dynamic viscosity. So this second coefficient of viscosity and dynamic viscosity, these two are making our some normal component into the stress tensor. That's why I am calling it as viscous normal stress, and this I am calling it as thermodynamic stress because of the thermodynamic pressure. All are clear with this idea? Is this point clear? So similarly, I will be having some normal stress in y direction. How much it will be? Minus p plus lambda times divergence of v vector plus 2 mu times del v by del y. Okay. Then I will be having sigma zz, which is minus p plus divergence of v vector plus 2 mu into del w by del z. One question, why I am not writing here px, py, pz? Pressure is a scalar quantity. It is equal in all the directions. Okay. This point is clear. Now, whenever I will be using this particular stress tensor for say my I is x now and j is y. So it means I will be calculating sigma xy. So sigma xy will become delta ij. I is not equal to j, so this term will become 0, and second term will be coming into picture now. Okay, so second term will become mu times del u by del y plus del v by del x. So that's why I am calling it as simply tau xy, because it is not including any contribution of non-viscous terms. It is purely because of the viscous terms. Okay. Is this point clear? So sigma over here I have defined the symbol for the total stress tensor, and tau I have defined the symbol for the tau is symbol for the shear. Shear plus normal, but because of the viscous component. Okay. So anything which is coming because of the viscosity of the fluid medium, that I am actually representing as tau tensor. Point is clear? All are clear with this idea? Okay. So similarly, if I write sigma yx, what it will be? mu times del v by plus del u by, and ultimately this is identical to this one. So I can say that tau xy is nothing but equal to tau yx is nothing but equal to tau xy. Okay. So it means that shear contribution of the viscous stresses is nothing but symmetric. Okay. So the symmetric stress tensor is called as, symmetric part of stress tensor is called as deviatoric stress tensor. Okay, so if I only write the stress tensor because of the viscous components, so I will be having tau xx, tau yy and tau zz. So this is only because of the viscous components. Okay, and here I will be having tau yx, tau zx, tau xy and tau zy. This will be tau xz and tau yz. So you can see the symmetry over here, that these two terms are identical to these two terms. This term is identical to this term. Okay. So this type of symmetric stress tensor is called as, symmetric viscous stress tensor is called as deviatoric stress tensor. What is clear? All are clear with this idea? Please tell me if anyone is having any doubt. If you are having doubt, please ask me. Is it clear? Okay, so now,
ऐसे तो हमारा total stress tensor भी symmetric ही होगा ना.
yes, but we have, whenever we actually remove pressure part out of that, then only we call it as deviatoric stress. Deviatoric stress is coming because, which is coming because of the viscosity. Okay. Remember one thing, whatever this formulation I am substituting, this is applicable only for Newtonian fluids. So once I will be substituting this particular formulation, then my fluid medium will be becoming purely Newtonian. Okay. Now, in this famous equation, one hypothesis was given, because if you have to solve this equation, so earlier your shear stresses or normal stresses were unknown, but now you have come to know the values of these stresses. Okay, what are these different stresses? So their values you have come to know. Once you have come to know the values of these stresses, you must also know the value of mu and lambda. You must also know the value of mu and lambda. Then only you will be able to do this calculation. Mu is very clear to us, which is popularly called as dynamic viscosity. But what about this second coefficient of viscosity, which is nothing but lambda? So if you add up all these terms, then ultimately we get one term which is called as 3 lambda plus 2 mu. I am not going into much details. This is called as bulk viscosity. Sorry?
So where are we getting 3 lambda plus 2 from?
I am not explaining that. So you just remember that this is called as coefficient of bulk viscosity, and this coefficient of bulk viscosity is considered equal to 0 by one famous person, Stokes. Okay, that's why it is also called as Stokes hypothesis. He mentioned that lambda plus 2 mu is equal to 0 and lambda is equal to minus 2 by 3 mu. Okay. From here lambda is coming equal to minus 2 by 3 mu. So this is called as Stokes hypothesis. When we introduce the Stokes hypothesis into the Navier's equation, then it becomes Navier-Stokes equations. Okay, so there were Navier's equations which were in the form of stresses, generalized form. Then we consider the Newtonian fluid. For Newtonian fluid we have supplied the formulations which represents the relationship between stress and strain tensor, and once we have converted that stress and strain tensor, we found some coefficients, and when to determine the values of these coefficients, we have used some hypothesis that is called as Stokes hypothesis. Now, if I substitute these formulations of the stresses as well as this hypothesis into the Navier's equation, whatever ultimately I will be getting, that will be nothing but my Navier-Stokes equation. The famous Navier-Stokes equations. The one very important point which you have to take care is these are applicable only for Newtonian fluids, because this lambda mu, what we are using the linear relationship, this is applicable only for the Newtonian fluids. If I go for non-Newtonian fluids, then this relationship becomes more complex. Then you have to add few more parameters. Okay, so that is why these equations are applicable only for the Newtonian fluids. Now, all of you please substitute this formulation into the previous component-wise equations, and in the next class show me the individual components of the Navier-Stokes equation. Okay, so that is our next task.